Welcome. Today's lecture is about millisecond pulsars. It so happens that most of what I'm going to tell you about today was the work done 40 years ago at the Raman Research Institute. The first millisecond pulsar was discovered by Don Becker and his collaborators 40 years ago in 1982. It was spinning 642 times a second. Can you imagine a star spinning 642 times a second? Well, this one was. Its period of rotation was 1.5 milliseconds. The discovery telegram by the International Astronomical Union indicated that it had a canonical high magnetic field of 10 to the power 12 Gauss. It was a solitary pulsar. It did not have a binary companion. This reminded me of the dog that did not bark. With a period of rotation of 1.5 millisecond and with a reported magnetic field of 10 to the power 12 Gauss, there should be a blazing nebulosity surrounding it, like the Crab nebula surrounding the Crab pulsar. But this pulsar was spinning nearly 30 times faster than the Crab pulsar. And since the luminosity of magnetic dipole radiation is proportional to the fourth power of the frequency of rotation, such a nebula would be 10,000 times more luminous than the Crab nebula and could be easily seen no matter where it was in the galaxy. But there was absolutely no nebulosity in radio, in visible wavelength, or in X-rays. And that reminded me of the story Silver Blaze. This very expensive racehorse was stolen, and the local inspector called Sherlock Holmes to come from London. And Sherlock Holmes spent a couple of hours going around with his magnifying glass, and then said, "Well, I'll now get back to London." The inspector was very surprised. He asked Holmes, "Is there anything that you wish to draw my attention to?" Sherlock Holmes said, "Yes, the curious incidents of the dog that night." Inspector Gregory said, "The dog did absolutely nothing that night." Sherlock Holmes replied, "That is the curious incidents." So the fact that there was no nebulosity surrounding this made me come to an immediate conclusion that the magnetic field of this pulsar must be many orders of magnitude smaller than what the initial observations had suggested. Now, here was a curious coincidence once again. If you remember, some lectures ago we discussed the Hulse-Taylor binary pulsar. And there I reminded you of what Miss Marple would have said about the curious coincidence. Here was a curious coincidence once again. It was a pulsar spinning at an ultra-rapid spin rate, and yet it had an extremely low magnetic field. As I said, this was reminiscent of the binary pulsar. The ultra-rapid spin rate suggested that it must be a very young pulsar, and yet its extremely low magnetic field, as conjectured by us, suggested that it must be a very old neutron star. So that was the mystery. But this one, unlike the Hulse-Taylor binary pulsar, was a solitary pulsar. Nevertheless, I was convinced that this pulsar too must be a recycled pulsar like the Hulse-Taylor binary pulsar. Let me quickly remind you of the recycling story. We have discussed this in great detail in an earlier lecture, therefore please permit me to do this rather fast. The bold conjecture made within 3 or 4 days after the discovery of the pulsar was the newly discovered millisecond pulsar must be a recycled pulsar. It is spinning fast because it was spun up in a binary system. It is solitary now because somehow it got rid of the companion. wild conjecture, isn't it? But wait. Now let's recall the story of the recycle pulsar. The reincarnation of the firstborn neutron star in a binary system. If you remember, in a massive binary, both stars explode as supernovae, leaving behind neutron star. Here we are talking about the firstborn neutron star. It is born spinning fast with a high magnetic field. It functions as a pulsar, and after a few million years dies due to various reasons. The idea of the reincarnation of this pulsar is that a dead pulsar is resurrected from its graveyard by being spun up to a very short period by accreting matter and angular momentum from the companion star. Now, to make a rapidly rotating pulsar with a weak magnetic field, which is what is demanded in the recycling scenario, two things must happen. One, the magnetic field of this pulsar must decay to a very small value. And two, the neutron star has to be spun up by accreting mass and angular momentum from the companion star. Now, I shall not discuss the magnetic field decay of neutron stars. It's a rather involved and subtle problem. We shall discuss that in a separate lecture because it involves superconducting and superfluid states in the interior of neutron stars, both being in vortex states. If you remember the lecture in which we took a journey to the center of the neutron star, there are two brands of spaghettis inside a neutron star. The Onsager-Feynman vortices parallel to the rotation axis and the Abrikosov quantized flexoids parallel to the magnetic axis. But we won't go into that in this lecture. Now, if you remember, I told you that a magnetized neutron star accreting from an accretion disk will attain an equilibrium period of rotation. Why? Now let us look at the accretion disk surrounding the neutron star, and this is a view, say, from the north pole of the neutron star. The green disk is the matter coming in from the companion. Because it has a high angular momentum, it cannot fall in radially, it will form an accretion disk. The point I had made was that the magnetic field will prevent the inner edge of the accretion disk from touching the surface of the neutron star. That is because the magnetic field exerts a pressure B squared over 8 pi. B, of course, is the dipole magnetic field, which decreases as 1 over r cubed. Now, at a distance from the neutron star, where the magnetic pressure B squared over 8 pi balances the ramp pressure of the incoming matter, rho v squared, the accretion disk will be arrested by magnetic pressure. The radius at which this happens is known as the Alfvén radius, named after the Swedish astrophysicist Alfvén. Now, the point was that a neutron star, which is spinning on its own, it could be spinning in any direction, it doesn't matter, will experience an electromagnetic torque due to the coupling between the inner edge of the accretion disk and the magnetic field lines which are anchored to the surface of the neutron star. This will make the star adjust its period of rotation such that the period of rotation of the neutron star will be equal to the Keplerian period at the inner edge of the accretion disk. Now, I won't go into the discussion all over again. Please refer back to the earlier talk. Now, that equilibrium period, which is just the Keplerian period at the inner edge of the accretion disk, is given by ... which we shan't bother right now, b to the power 6 over 7, and m dot to the power minus 3 over 7, where m dot is the rate at which matter is accreting onto the surface of the neutron star from the inner edge of the accretion disk. It flows along the magnetic field lines to the north and south magnetic poles. The idea was that the dead neutron star, which has long been buried in the graveyard of neutron star, is resurrected from the graveyard by being spun up, and it is spun up to an equilibrium period. And that equilibrium period is determined solely by its magnetic field and the accretion rate. Larger the magnetic field, longer will be the period. Larger the accretion rate, shorter will be the period. Now the question is the following. Now listen to me carefully. Look at that formula. Greater the accretion rate, shorter the equilibrium period. Now this is a plot of the logarithm of the magnetic field along the y-axis and the logarithm of the rotation period along the x-axis. Now for a fixed accretion rate m dot, in the log-log plot, the equilibrium period will be a sloping line of a slope very nearly equal to 1. Therefore, a neutron star accreting at a rate for which this is the equilibrium period will be spun up to that period. If the accretion rate is larger, then it will be spun up to a shorter period. If the accretion rate is even larger, then it will be spun up to an even shorter period. So, higher the accretion rate, shorter will be the equilibrium period. Now let's look at the other factor. Smaller the magnetic field, shorter the equilibrium period, because the magnetic field comes in the numerator on the right-hand side. Therefore, for a given accretion rate m dot, if the magnetic field is that value, then the neutron star will be spun up to that period. That will be the equilibrium period. But on the other hand, if the magnetic field of a neutron star is much smaller, then it will be spun up to a much shorter period. Therefore, the question is the following. You are given a neutron star with a magnetic field. It has decayed to that value when it is being resurrected from the graveyard. The question is this: can we spin it up to an arbitrarily short period by going on increasing the accretion rate from the companion star? So, if the accretion rate is that, the neutron star will be spun up to that period. If the accretion rate is there, it will be spun up to a shorter period. If the accretion rate is even larger, it will be spun up to an even shorter period. The question is there a limiting value to the equilibrium period? Or in other words, is there a maximum value to the accretion disk? And this is what I told you in the earlier lecture when we discussed the Hulse-Taylor binary pulsar. When matter falls onto a neutron star, say an electron or a proton or a mountain, it will emit X-rays. The gravitational binding energy release is roughly 10% of the rest mass energy. And the luminosity of the X-rays generated is some efficiency factor eta, which is 10% or so for neutron star, m dot c squared. Okay? Please remember, mc squared is the energy, m dot c squared is the energy liberated per unit time, or the luminosity. So we are asking the question, is there an upper limit to the accretion rate? And the answer is, yes, there is an upper limit. There is an upper limit for the following reason. If you remember what Eddington taught us way back 100 years ago, that there is a maximum luminosity to a star which is in radiative equilibrium. And that maximum luminosity, which is known as the Eddington luminosity, is 10 to the power 38 ergs per second into mass of the star divided by mass of the sun in solar mass units. This is one of the most remarkable formulas in physics because this says that the maximum luminosity a star can have is determined apart from fundamental constants solely and uniquely by the mass of the star. Therefore, since there is a limiting luminosity for the X-rays, there must be a limiting luminosity for the accretion disk. For example, if the star were to accrete at a greater rate, then the luminosity of the X-rays it generates will prevent matter from accreting at a greater rate. That limiting value of accretion rate, which is known as Eddington accretion rate, is approximately 10 to the power 17 grams per second, roughly 1 Mount Everest worth of matter per second. So although the companion star may be willing to give you a lot more mass, the neutron star will not accept more than 10 to the power 17 grams per second, because if it did, then the luminosity of X-rays it generates will push the matter away and prevent it from accreting onto the neutron star. Therefore, there must be a minimum value for the equilibrium period corresponding to the maximum value of the accretion rate, and that maximum value for the accretion rate corresponds to the Eddington luminosity of the X-rays generated in the accretion process. And that Eddington accretion rate is 10 to the power 17 grams per second. So if I put in that value of 10 to the power 17 grams per second for m dot in that formula, these are the dot 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 consists only of fundamental constants, and therefore the limiting value or the minimum period to which you can spin up a neutron star by accretion is given by this beautifully simple formula: 1.9 milliseconds, multiplied by b in units of 10 to the power 9 Gauss to raise to the power 6 over 7. Therefore, if the magnetic field of the neutron star is 10 to the power 9 Gauss, then the minimum period to which it will be spun up will be 1.9 milliseconds. If the magnetic field is more, the minimum period will be larger. If the magnetic field is even less, then the minimum period will be even shorter. So that was the idea. So let's go back to this. So what one is saying is you can go on increasing the accretion rate till you hit the Eddington value of the accretion rate. That is the minimum equilibrium period to which you can spin up a neutron star by accretion. Now, the beautiful thing about this idea is that, once again, let us look at the plot, which is the logarithm of the magnetic field on the y-axis against the logarithm of the rotation period on the x-axis. This red line is the equilibrium period spin-up line, corresponding to the Eddington accretion rate. And that is a sloping line because the equilibrium period is proportional to b to the power 6 over 7. Therefore, in a log-log plot, it will be a sloping line. So if the neutron star's magnetic field doesn't decay at all, it will be recycled to that period. If the neutron star its field has decayed to that value, then it will be recycled and spun up to that equilibrium period, like the Hulse-Taylor binary pulsar. But if the magnetic field of the neutron star has decayed to a much smaller value, then it will be spun up to a period of the order of a millisecond. So the equilibrium period is really determined by the magnetic field. So let's look at this plot once again. Log of the magnetic field against the log of the rotation period. This is the critical equilibrium period line corresponding to the Eddington accretion rate, and that circle, blue circle, 1913 plus 16 is the famous Hulse-Taylor binary pulsar for which the Nobel Prize was awarded in 1993. The IAU telegram suggested that the millisecond pulsar discovered on 2nd November 1982 was sitting over there where the cursor is pointing. Its magnetic field was 10 to the power 12 Gauss. But according to us, it should really be very close to this line. That if the millisecond pulsar was recycled and spun up to a minimum equilibrium period corresponding to the Eddington luminosity accretion rate, then it should not be sitting there, but future observation should show that it should really be sitting there. So within 5 days after this pulsar was discovered, we wrote a paper in which we asserted that this millisecond pulsar, although it is a solitary pulsar, unlike the Hulse-Taylor binary pulsar, must be a recycled pulsar. Its magnetic field cannot be 10 to the power 12 Gauss. Its magnetic field must be 5 times 10 to the power 8 Gauss. And its period derivative must be 10 to the power minus 19 seconds per second. The early observation suggested that the period derivative was 6 orders of magnitude larger. So we suggested that the period derivative must be, in fact, 10 to the power minus 19 seconds per second. Now, roughly 4 months after these predictions were made, Andrew Lyne and his collaborator at Jodrell Bank Radio Telescope in Manchester accurately measured the period derivative of this pulsar and therefore the magnetic field of the pulsar. The period derivative of the pulsar was 1.05105 10 to the power minus 19 seconds per second, and the magnetic field was 4.7 times 10 to the power 8 Gauss. So the prediction we had made 4 months earlier was that the pulsar should really be sitting over there, and its magnetic field should be 5 times 10 to the power 8 Gauss. The observed value of the magnetic field turned out to be 4.7 times 10 to the power 8 Gauss. So here it is in all its glory, the period of the millisecond pulsar and the period derivative of the millisecond pulsar. We had predicted it will be 1 times 10 to the power minus 19 seconds per second. It is 1 times 10 to the power minus 19 seconds per second. Before we move on, the period of this pulsar has been determined to 17 decimal places. Why only 17 decimal places? Because the unit of a second, unit of time, namely the second, is defined only to 17 decimal places. The unit of time is defined in terms of the frequency of a line, if I'm not mistaken, of the cesium atom. And that is known only to 17 decimal places. Therefore, this pulsar is actually now used to cross-check the stability of the 3 atomic clocks, one in Washington, D.C., one in Stuttgart in Germany, one in Paris in France, which define the standard of time. Because the long-term stability of this clock is greater than the long-term stability of atomic clocks which are subject to stochastic quantum fluctuations. Now we turn to a rather interesting question. Where do these millisecond pulsars come from? The Hulse-Taylor pulsar came from massive binary system, whose mass initially were about 25 times the mass of the Sun and 10 times the mass of the Sun. But that cannot be the case in this case. Why? Because if a millisecond pulsar had been spun up, and it has been spun up to a period of 1.5 milliseconds, then it is an enormous amount of rotational energy, half I omega squared, and angular momentum, I omega. That you cannot achieve without accreting roughly a tenth of a solar mass of material from the companion star. But please remember, although the companion star is happy to give you as much mass as you want, the neutron star cannot accept more than 1 Mount Everest per second, 10 to the power 17 grams per second. Therefore, in order to accrete 0.1 solar mass of material, the neutron star must have accreted at least for 10 million years, even at the maximum Eddington accretion rate. The Eddington accretion rate is roughly 10 to the power minus 8 solar mass per year. Therefore, the progenitor of the millisecond pulsar cannot be a massive companion, because a massive companion will give its mass very quickly in the time scale of about 100,000 years, and the story will be over. The massive star will explode as a second supernova explosion. So the companion star, we argued, must be a star which is less massive than the neutron star. The neutron star has a mass of 1.4 solar mass, the Chandrasekhar limiting mass. Therefore, we are talking about a companion star like the Sun, or even less massive than the Sun. So this was a prediction made in 1982 that the progenitors of the millisecond pulsar must be low-mass X-ray binaries. Now, here is something that a beautiful piece of physics that is involved. And I want to remind you about two problems that I asked you to do when we discussed the Hulse-Taylor binary pulsar. I told you that let's assume that no mass is lost from the system. Mass can only go from star 1 to star 2 or star 2 to star 1. Conservative mass transfer. I asked you to verify that when a more massive star transfers mass to a less massive star, the orbit will shrink and the accretion will be a runaway accretion. I also asked you to verify that when the mass donor is the less massive of the two stars, the orbit will expand, and therefore there will not be a runaway mass transfer. But if the orbit expands, maybe mass transfer will stop. But you want the mass transfer to go on at least for 10 million years, if not more than that. So when the mass donor is less massive star, the orbit will expand. So there will not be a runaway mass transfer, which will be over very quickly in a thermal time scale of the order of 100,000 light years. Now, even as the orbit expands, the orbit will shrink because gravitational waves are being emitted. Remember the shrinking of the binary orbit of the Hulse-Taylor binary pulsar due to gravitational radiation? Similarly, if you have a neutron star and a low mass star going around a common center of mass, gravitational radiation will be emitted, and that will make the orbit shrink. Therefore, there are two opposing effects. One is the orbit will expand because the less massive star is transferring mass, and the other is the orbit will shrink because of gravitational radiation is carrying away energy and angular momentum. So there will be, as a result of the combination of these two effects, there will be a controlled mass transfer for hundreds of millions of years. And it is possible, we argued, that this can be spun up to a period of 1.5 milliseconds. And that prediction was made in 1982. In 2013, this remarkable discovery was made, nearly 35 years later. Here was an X-ray binary consisting of a low-mass star transferring mass, Here is a low-mass star where I'm pointing, transferring mass to a neutron star, and this is the accretion disk. The neutron star is at the center, and the neutron star is emitting X-rays. Now, this particular low-mass X-ray binary, believe it or not, Mr. Jekyll transformed himself into Dr. Jekyll, transformed himself to Mr. Hyde in 2009. The X-ray switched off, the accretion switched off, and what you had, lo and behold, was a millisecond radio pulsar. And that's not all. This system was followed. And it goes back and forth. In 2013, after spending 12 years as a radio millisecond pulsar, it is now back functioning as a low-mass X-ray binary. So this transient millisecond pulsar, which was reported around 2013 or 14, 35 years after we had made the prediction, confirmed that several millisecond pulsars have now been found which switch between radio pulsar state and a low-mass X-ray binary state. And therefore the smoking gun has been found, and the progenitors of millisecond pulsars are now proved to be low mass X-ray binaries, as was predicted nearly 40 years ago. Now, what happened to the companion of the millisecond pulsar? If it was a recycled pulsar and if it went through all this fascinating binary history, where is the binary companion? Well, we waved our hands in our 1982 paper and said somehow this binary companion must have been blown away by the pulsar. Well, so the argument we made was the companion must have been blown away by the millisecond pulsar. The evidence for this came 6 years later when an eclipsing millisecond pulsar was discovered in 1988. And here is the eclipsing millisecond pulsar. There is a low mass white dwarf which is going around, that is really going around a common center of mass, but for the sake of simplicity, I have shown it here as going around the pulsar. Now, the pulsar's lighthouse beam is in the plane of the orbit. Here we are looking at it from the Earth. So every time the pulsar beam is sweeping once every 1.5 milliseconds or so. But every now and then the white dwarf comes between us and the pulsar, so the pulsar is eclipsed. So this is an eclipsing millisecond pulsar. So what radio astronomers found was that so what you have in this cone is a relativistic beam of particles emanating from the polar cap of the pulsar. Remember, we discussed that. Particles are pulled out of the surface due to electric field, due to potential drop of 10 to the power 16 electron volts, and accelerated to the speed of light. So that electron and proton beam is going out in a narrow cone, and that narrow cone is hitting this white dwarf once every orbital period. And there is clear radio astronomical evidence that the relativistic beam and the hard radiation from the neutron star are ablating the white dwarf. And theoretical astrophysicists have estimated that in a few million years, if this goes on, the white dwarf would be completely ablated. So once in a while, if the relativistic beam from the neutron star is intercepted by the companion, then, and this can happen once in a while, and here is a case where it is happening, then the companion could have been blown away. And that could have been the case of the first millisecond pulsar. This one, of course, was not solitary. There was no argument about this being a recycled pulsar. A couple of years later, a second millisecond pulsar was found. This was in 1988, but a little earlier to that, in 1986, the second millisecond pulsar was found. This was the third millisecond pulsar. A second millisecond pulsar was found. This one was in a binary. Its orbital period was nearly 120 days. And the companion was a low-mass white dwarf with a mass of the order of 0.8 times the mass of the Sun. The discovery of this binary millisecond pulsar provided definitive proof for the recycling scenario. But the skeptics were not convinced by any of these arguments. In March 1986, the third millisecond pulsar was discovered. This immediately suggested that there must be a very large population of millisecond pulsars exceeding many tens of thousands, perhaps hundreds of thousands. I won't go into the argument for how we came to this conclusion. And therefore, soon after this third millisecond pulsar was discovered in 1986, Dipankar Bhattacharya was a young student at that time working with me, and I wrote a paper making several bold predictions. One of them was the following. The population of low-mass X-ray binaries, which are the progenitors of millisecond pulsars, Of course, at that time, there was no proof, because the proof came only around 2013. We are talking about 1986. We had claimed were low-mass X-ray binaries. There are only 125 low-mass X-ray binaries in the galaxy. They are so powerful that you can see them wherever they are in the galaxy, and the number is around 125. So how can 125 parents account for offsprings which may be 10,000 in number or 100,000 in number? This is only possible if the lifetime of the offspring, namely the millisecond pulsar, is 100 times longer than the X-ray phase of the low-mass X-ray binary. In other words, the offspring lives 100 times longer than the parent. And that would account for this discrepancy. And from this we argued that millisecond pulsars therefore must live forever. If millisecond pulsars must live forever, it implied that their magnetic field cannot decay any further. It has reached some asymptotic value. The physics of that asymptotic value is once again connected with the coupling between superconducting and superfluid phase in the interior of neutron stars, and I do not have time to go into that in this lecture. Now, the predictions that were made in 86 were the following. Most millisecond pulsars will be in binaries with low mass companions, and their orbits will be circular. Millisecond pulsars, all millisecond pulsars, will have magnetic field of the order of 5 times 10 to the power 8 Gauss. Their rotation periods will be between 6 and 10 milliseconds. So these were the 3 predictions that were made when the third millisecond pulsar was discovered, and before the third pulsar's magnetic field was measured by radio astronomers. So, famous Chinese saying that I am fond of, one picture is worth 10,000 words. So let me repeat what I said using this figure. Here is our familiar log B plot, and the green line is the critical spin-up line corresponding to accretion at the Eddington limiting value. A pulsar is born and it dies a natural death, and its field has decayed to an asymptotic value. This was a conjecture. Magnetic field doesn't decay any further. Then, due to accreting mass and angular momentum of the companion, it is spun up to the minimum possible equilibrium period, which is on the green line. And then when the companion ceases mass transfer, and you can see the neutron star functioning as a radio pulsar, it will begin its normal life. So we would expect all millisecond pulsars to be in this red oval, with the dots are the predictions of where you will find millisecond pulsars. So the prediction was the majority of millisecond pulsars will be in circular binaries with periods between 6 and 10 milliseconds, and their magnetic fields, all of them, will be 5 times 10 to the power 8 Gauss. 30 years later, here is the data. So that is to just remind you of what I have just said, summary of the predictions, and here is the modern data. Once again, it's a plot of log of the magnetic field versus the log of the spin period, and there are some 2,500 pulsars here. Look at the pulsars inside the red circle. There are nearly 100 binary millisecond pulsars inside that. All of them in circular orbits. The eccentricities of some of them is as small as 10 to the power minus 5. As someone said, as spherical as a Mercedes-Benz ball bearing. And look at it. All of them have magnetic field of the order of 5 times 10 to the power 8 Gauss. So this is and that green line is just to aid your eye, is where the critical equilibrium period line is sitting. So almost all the 100 binary pulsars are bang on the equilibrium period line, and their magnetic fields are 5 times 10 to the 8 Gauss, and their periods are between 6 and 10 milliseconds. Now, let us turn to a more recent interest in millisecond pulsars, and that is because they are potentially sources of gravitational waves. Well, we discussed in the previous lecture gravitational radiation. If you remember, the energy lost due to gravitational radiation per unit time is given by this quadrupole formula. It is proportional to the square of the third time derivative of the quadrupole moment. For dipole radiation, it is d double dot whole squared. That is Rayleigh's formula. For quadrupole radiation, it is q triple dot whole squared. This is true regardless of whether you're talking about an electric quadrupole, a magnetic quadrupole, or a gravitational quadrupole. In this case, we are talking about the luminosity of gravitational radiation. So the lowest order gravitational radiation is due to quadrupole moment. As matter, so the gravitational wave detected in 90 events so far. The first one was September 15, 2015, almost on the dot to mark the centenary of the publication by Einstein of his new theory of relativity. That is due to the coalescence of 2 black holes which spiraled in. And then came the coalescence of 2 neutron stars which spiraled in and coalesced. Here we are talking about gravitational radiation from a neutron star. And the origin of the neutron star is a little mountain, little blister on the surface of a neutron star. As matter accretes on the magnetic poles from the inner edge of the accretion disk, a little mound will form, and that will give it a quadrupole moment, which will be time varying, and therefore there will be gravitational radiation. And the luminosity of that gravitational radiation will be proportional to the 6th power of the frequency. That comes from over there. If the quadrupole moment is changing with an angular frequency omega, then I take 3 derivatives and then square it, then the luminosity will be proportional to the 6th power of the frequency. Therefore, if I have a little mountain on a neutron star, which makes it non-spherical, then it will radiate. And because it is spinning with a period of 1.5 milliseconds or thereabout, the luminosity can be significant. And unlike in the case of a coalescing binary, the frequency of this radiation always remains the same, which is equal to the frequency of rotation of the central star. And therefore, you can build a resonant detectors. So the hope is the next generation LIGO, Virgo, and other detectors should be able to detect gravitational waves from millisecond pulsars. This is why I'm talking to you about a very old story today. Although millisecond pulsars were discovered 40 years ago, suddenly there is a great deal of interest in them because they are potentially sources of gravitational waves. As neutron star is spun up to a period of millisecond, the gravitational wave luminosity could be significant. And the recently discovered transient millisecond pulsars are very good candidates for LIGO and other instruments. You know where to look for. So this system, for example, which is accreting from the companion star, is a very good candidate for resonant detection of gravitational waves. Therefore, the prospects are good for detecting gravitational waves from accreting millisecond pulsars. Well, I won't go into this, but just to whet your appetite, there was another prediction that I had made way back in 1988. I had predicted in a conference in June 1988, a long time ago, that there will be a new population of gamma ray sources that will be discovered. And this population will consist of millisecond pulsars. They will not only be radio pulsars, they will be gamma ray emitted. That was in 1988. In August 2009, the Fermi Large Area Telescope on board the NASA Fermi Gamma Ray Telescope detected nearly 100 millisecond pulsars. The number is actually close to 150 now. So those are the millisecond pulsars emitting gamma rays, as was predicted way back in 1988. So with that, we shall conclude this lecture on millisecond pulsars. Do go back to the lecture on the Hulse-Taylor binary pulsar and review what we discussed about equilibrium period and Eddington luminosity limit. In the next lecture, we shall be discussing supernovae and cosmic rays. Till then, thank you for your attention.